This is the third lecture for Chapter 16, Acids and Bases, and we'll finish it up with this one. I think we already mentioned this one for for the weak acids, so I'll just move on past this. We're doing this process the exact same way again. We're looking at a problem here. What is the pH of a concentration of ammonium? So we have this equation listed here. Here is our expression, our equilibrium expression. We know what the Kb value is here. So going back to our initial equation, we are going to have some change in there, but we just know that when we go through here, the change is equal to these values for our products. Remember, this is going back and forth. And whatever I happen to lose out of the reactant is negligible, so I really still have this value here. Going into the Kb expression, if we substitute those values in, we solve for x, and this is our OH concentration. So if I want to know what the pH is, we'll just go into this expression. We'll take a POH, which gives us this value here, but I don't want the POH, I want the pH. So if I subtract it from 14, you get the value in the bottom. So not too bad. And again, you'll do lots of examples of this and it'll come. So looking at some comparisons of some values here, let's see if we have a good one here. Let's go with hydrofluoric acid. It's a pretty weak acid. We see its value here. And if we make the comparison for its Kb, we have this here. Notice if you multiply those two values out again, you get the Kw. And the Kw is 1 times 10 to the negative 14. So once you know one, you can get the other. Okay. Won't mention much with this one right now. We'll see this as we play out here in the next couple slides. So I guess we're there. Examples. Some things that sound kind of weird that we haven't really talked about yet is some metals actually can act as acids. Not in a direct way, it's somewhat indirect. A lot of times when you put metals into solution, they become hydrolyzed, as you saw in the previous slide. So it forms what's called a complex. So you end up with the metal ion surrounded by a certain number, and it can vary depending on the metal, of water molecules. So the metal is actually attracting, as you can see in the picture above here, the metal is positive, in this case is positive 3, so it's attracting the negative side, or the water oxygen, to it. So as enough of these are approached on there, say 6, it's going to pull the electron density away, and then eventually a hydrogen ion can pop off and form a hydronium ion in solution, which forms an acidic solution. So it's another way an acidic solution can form. And we've already kind of mentioned this. So one of the things to look at in regards to how do I know if I'm getting an acidic solution or not from a metal? Well, as a general rule, when you're looking at some of these metals, and typically they're transition metals, not group 1s or group 2s, but in the middle block of the table, you have some of your transition metals. The plus 2s are going to form acidic solutions. Notice these values are rather low. And then as the charge, that's the main thing we really want to focus on, not so much the size, but as the charge of the metal ion goes up, it forms an even more acidic solution. So an iron 3 plus solution is significantly more acidic than an iron plus 2 solution. Okay? So some general rules. We won't go too far with this, but you have them in the book as well. You can kind of read through these, some things that affect the acidity or not, the pH of a solution. Just reading through those. Again, I don't want to spend a lot of time on those, but here's a couple examples, and the book does a pretty good job as far as going through them as well. So it does take some time to go through them, and we will mention them in class. There's an example or two in the homework. And this is a continuation of that list. Some other things that affect the acid strength is the polarity of the atom that happens to be attached to. And you're quite familiar with that, for example, fluorine is the most electronegative of them, but it has to do with the polarity of the bond as well. So notice, for example, that hydrofluoric acid is a relatively weak acid, and then as you go down the list, they become more acidic. So the question is why? Well, it has to do with the polarity of the bond. So we say, for example, that last one we just mentioned, moving from the top to the bottom, the radius becomes larger of the atom, so therefore the bond becomes more polar, and it's more easy to break apart that hydrogen from that other atom. I was going to say central atom, but other atom. And we can also mention in regards to moving from the left side of the table to the right side of the table, the electronegativity increases, so therefore that atom or that bond is going to become more polar, and the same principle takes place, is that the hydrogen is going to be removed from that atom much more easily. You're not having a covalent bond, you're having a very polar bond, and the hydrogen breaks up. So a misconception is that hydrofluoric is a very strong acid, and it's not. It's relatively weak. It's almost to the point that because the fluorine is so electronegative that even if it was potentially possible to remove the hydrogen, and it is, it actually just reattach it because it's positive to negative attraction. Another example, something we can look at in regards to how a hydrogen is pulled apart, is the, trying to find the words, the electronegativity of that particular atom again. So if we compare these oxy acids, we can see that the hypoiodous acid listed down here is a relatively weak acid compared to the hypochlorous acid. It's relatively higher in comparison. And the reason for this isn't so much the idea of the electronegativity connected directly to the atom, it's more about the pull that these particular atoms have. So as an example, we'll do hypochlorous acid. In every one of these cases, the hydrogen is attached to the oxygen. Well, as this is more electronegative, the chlorine is more electronegative than the others, it is pulling the electron density more so towards the chlorine, and therefore this is isolating the hydrogen more so, making it more easily removed. So this is more electronegative than the two below, so therefore it is going to be a stronger acid. And this is just what we mentioned there. Well, I guess to take that back, as you add more oxygens to the group, so here's my central atom, chlorine. As I add more oxygens on the peripheral of that chlorine, again, the electron density is being pulled further and further away from this hydrogen, and therefore it is going to be more easily removed. And one other thing in regards to acids, somewhat unusual ones out there, but they're, well, I shouldn't say they're unusual, they're actually quite common, is the carboxylic acids. These are organic, and you talk about them in organic chemistry. What makes them interesting is because they have this resonance, they're quite stable as a conjugate base. So that's why once the hydrogen is removed, they don't seek it out per se. I mean, this is electronegative, right? So it should be attracting a hydrogen. It has all these electron pairs to accept it, but it doesn't. And because of this resonance, when it's looking for electrons, it can get it from the opposing double bond. All right, last one on here, Lewis acids and bases. This is may or may not be on the AP exam, but we are definitely going to mention it in our class. It's one last, most broadly viewed way to look at acids and bases. All you have to do is flip the perspective in regards to what an acid or a base does. Typically, when we talk about acids and bases, we say an acid donates a hydrogen and a base accepts it. Just flip it a little bit. No longer is an acid going to donate, an acid is going to accept. So here's another way of taking a look at a Lewis acid and a base. And we'll go a really basic one here. We'll take a look at HCl. So HCl we just typically look at as an acid. But what's the acid and what's the base in regards to Lewis? Well, we know that we're going to be getting these as products, H plus and Cl minus. So if I want to just look at this in regards to the electron pair that's between these two, chlorine or chloride is going to act as the Lewis base in this example, that it is going to be accepting the electron pair, and the hydrogen ion is going to be acting as the acid, which is going to be donating the electron pair. So notice the example we can point to over here. Well, there we have the chloride with the electron pair. It has accepted that electron pair, and hydrogen has donated the pair and has gone off on its merry way.